Hi, and welcome to the 6.1 Stoichiometry notes video. This is an intro to stoichiometry. During this video, you will be taking notes on this note sheet, so feel free to pause it when necessary to copy down the notes. And if you miss something, you can always rewind it. All right, let's get started. So our objectives are to define stoichiometry and to determine appropriate mole ratios to use for a stoichiometry problem, and also show you how to use them. How to use the mole ratios in 3 examples. So first off, what is stoichiometry? Make sure you copy this definition down. Stoichiometry is using mole ratios to convert from the amount of one substance, which is your given, to the amount of a different substance, which is what you're asked to find. So again, if you need time, make sure you pause the video to copy the definition down. One key point of this definition is that what you're starting with will be a different substance from what you're ending with or asked to find. So that's when you use mole ratios, is when you're not starting and ending with the same exact substance. But they are related through mole ratios. So let's now define a mole ratio. A mole ratio, just like with any ratio, is a proportional relationship. And this is between the moles of 2 different substances that is used as a conversion factor in stoichiometry problems. So we use ratios often. For example, one example of a ratio is, we would say, 4 quarters in a dollar. So that's a 4-to-1 ratio. And you can do the same thing in science when you're dealing with substances. And remember, the central unit for amount in substances, particularly in chemistry, are moles. So when we want to relate things, we're going to relate the number of moles of different substances. And so that's where mole ratios come in, and they can be used as a conversion factor. Now, there are 2 different types of stoichiometry problems based on the type of mole ratio that is used. So let's take a look at that, and then we'll also look at how to get mole ratios from these 2 types of problems. And that will give us a better sense of what a mole ratio is. So we know it's a proportion, but what exactly does it look like, or how do we express it? So the first type of stoichiometry problem is what's called compositional stoichiometry. And in a compositional stoichiometry, the mole ratio comes from subscripts in the chemical formula. So when I say a chemical formula, H2O is a chemical formula. It's the chemical formula for water. And we would use the subscripts, either the 2 for the hydrogen or that invisible 1 for the oxygen, to help us with our mole ratios. So in this example, it says, how many hydrogen atoms are there in 5 grams of H2O? So first of all, what are the substances that I'm trying to relate or convert to and from? Well, the substances are water and hydrogen atoms. And if you look at water, you know that for 1 water molecule, I'm going to write this down. This is not my mole ratio, but it'll show us where we get it from. So for 1 water molecule, we have 2 hydrogen atoms, right? So for every 1 water molecule, we know we have 2 hydrogen atoms because of that subscript. So how do we express that as a mole ratio? To express that as a mole ratio, instead of saying 1 water molecule, we're going to scale everything up to a mole. So what if we had 1 mole of water molecules? So 1 mole of H2O. How many hydrogen atoms would we have then? Well, we would have 2 moles of hydrogen atoms because of that 2-to-1 ratio. That subscript 2 tells me for every 1 water molecule, I would have 2 hydrogen atoms. So if I had 1 mole of water molecules, I would have 2 moles of hydrogen atoms. And we can express our mole ratio with an equal sign in the middle. Okay? So this is our mole ratio here. This is our mole ratio for this example. Okay? So again, in compositional stoichiometry, it's you get it from the subscripts. Let's now look at reaction stoichiometry. In reaction stoichiometry, we're dealing with a chemical reaction. And in this case, we're going to use, for our mole ratio, we use the coefficients in a balanced chemical equation. So let's take a look at this example. It says, how many grams of hydrogen, or H2, do you need to make 5 grams of H2O, or water, according to the reaction? And here's the reaction. It's a synthesis reaction. 2 hydrogen molecules plus 1 oxygen molecule makes 2 water molecules. We can also read this as saying 2 moles of hydrogen molecule and 1 mole of oxygen molecule make 2 moles of water molecules. And so in this case, what we're trying to find the relationship between is H2 and H2O. Those are our 2 substances that we're looking at. So look for the chemical formulas and then you know your substances. All right, and according to the balanced chemical equation, if you look at where they're here, we have H2 and H2O. It's a 2 to 2 ratio. So 2 moles of H2O and 2 moles of hydrogen gas, or H2, and 2 moles of H2O. So our mole ratio here is going to be 2 moles of H2 is equal to 2 moles of H2O. Now I'm writing these as equations to show that they are equivalent according to the coefficients here. You can also use the the two dots, that's called a colon, right? You can use a colon to express ratio, or you can write the word TO in between, just the same way you always express ratio. But later we're gonna take this and make it into a conversion factor fraction with dimensional analysis when we go over the examples. Okay, so that's how we get our mole ratios. If it's compositional stoichiometry, use the subscripts. If it's reaction stoichiometry, use the coefficients in the balance equation. Now for most of this unit, we're going to focus on these, reaction stoichiometry, but I will show you what compositional stoichiometry looks like. Now that we've gone over the basics of stoichiometry, what I want us to do now is look at the steps for solving these problems. So if you can, take a moment, pause the video now and read through the steps, and then we'll go over them together. So the first step, which is our step 0, is kind of getting us set up. You're going to read the problem, identify your given and find, and then you're going to map out a plan by following the steps below. Now, one thing that's also important, if you're dealing with reaction stoichiometry, you must make sure you have a balanced chemical equation. So if the chemical equation is not balanced, go ahead and balance it. All right, so here's our first step. Take a look at your given. If the given is not in moles, so the amount of given, let's say, is in grams or is in molarity, which is not moles, then you're going to use the mole map equations to convert the amount of given into the moles of given. And remember, we did the mole map last unit. Once you have your given in moles, your second step is to convert moles of given to the moles of find using your mole ratios in dimensional analysis. And then the third step is if you're asked to report the find in something other than moles, because right now in step 2 you have the moles of what you're asked to find, the substance you're asked to find. But let's say they want the mass of what you're asked to find. Then once again you're going to use your mole map equations to convert from moles of find into the amount of find as requested. So taking a look at the steps here, what does that sort of look like? This is sort of our map here. So let's label that our map. All right, so this first part is our step 1. If you're given the amount of given is not in moles, you're going to convert from amount of given to moles of given. And that's your step 1. And you're going to use the mole map equation. And then the next step is to go from moles of given to moles of find. And for this step, we're going to use our mole ratio, like we did above. Now the thing to remember is that your mole ratios will either come from subscripts or coefficients. The other thing I want to note here is that at this point is where we're going to be using dimensional analysis. To do that conversion from moles of given to moles of find. The last step, if they're asking for your find in something other than moles, is once again we're going to go to the mole map. To do that conversion. So now that you have this, once you have this copied, I also want you to copy down the mole map equations, where remember we have moles in the center. And if you want to convert from moles to mass, you're going to use this equation, mole equals mass over molar mass. If you want to convert from to or from moles and number of atoms or molecules, this is number of atoms or molecules, you're going to use 1 mole is equal to Avogadro's number, 6.02 times 10 to the 23. If you want to convert from moles to molarity or vice versa, you're going to use molarity is equal to moles of solute over liters of solution. And if you want to convert to or from moles and the pressure, volume, or temperature of an ideal gas, you're going to use PV equals nRT equation, where R is that gas constant 0.821 liters atmosphere K mole. I'm going to go ahead and zoom this in so it'll make it easier to copy. So you're going to copy down this information, and when you're done, go ahead and press play again. Okay, so now that you have all the information that you need sort of as your setup, the next video I will walk you through examples. We'll start with compositional stoichiometry, reaction stoichiometry, mole to mole, and then reaction stoichiometry, mass to mass. All right, that's it for this video, part 1, and then in part 2 we'll look at the examples. Have a quality day.